So today we are going to discuss about Ohm's law and resistance, conductance, resistivity, conductivity. It's a very important concept. Let's get into the chapter. Here, here we are seeing a conductor which is having a length L and a potential is applied between the ends of the conductor and let it be V, due to which the current is flowing through the conductor. This is the direction of current flow, and this is the direction of flow of electrons. And inside the conductor, we know everything is made up of atoms. So this is a microscopic view inside the conductor, and there are more number of atoms and free electrons. And the electrons, when they are moving inside the conductor, definitely they will be colliding with the atoms as well as with the other electrons which are present inside the volume of the conductors. Okay. Now, when the ends of the conductors are connected to a cell of potential V, then the free electrons are driven by the applied voltage and the current flows in it. Suppose if we give you a potential, this potential is nothing but the amount of work done to move the electrons from this end to this particular end. And we know that the direction of conventional current is always opposite to the direction of flow of electrons. When the potential difference between the ends is doubled, what happens inside the conductor? Suppose if the potential is doubled, for example, initially there is 5 volt, say a current of 2 ampere is flowing. Suppose if the potential is doubled, suppose now it is 10 volt, the current is also doubled, which means that V and I are proportional to each other. So we can write V is proportional to the current I, and the proportionality constant can be included in case of equating these two factors. So V is equal to a constant of proportionality or into I, so which represents the relation between current, voltage and resistance. But actually this is not the equation of Ohm's law. This equation is used to calculate the potential, or it is used to calculate the resistance, or else it can be used to calculate the current flowing through the conductor. But the statement of Ohm's law is not connected with this particular equation. This is one of the form of Ohm's law, and this is not this equation which connects the statement of Ohm's law. Okay. So for that we have to go for current density, conductivity and the electric field intensity, how they are related with each other. So by knowing these factors, we can easily understand the statement of Ohm's law. Okay. Here R is known as the constant because each and every conductor has its own resistance. If you consider this as a copper conductor, it has its own resistance. If you consider this as another material, suppose aluminum, it has its own resistance. Okay, so what do you mean by resistance? Actually, the resistance word means that it is a opposition offered to the flow of electrons. Suppose if there is an electron flowing from this end to this end, so due to collision, the path of the electron will not be a straight line as shown here. Suppose if there is no resistance inside the conductor, if the conductor has zero resistance, then the path of the electron will be a straight line. No doubt, without any collision, the electrons can move. But this is not the actual case. Each and every conductor has its own resistance, and when the electrons collide with each other. Due to collision, the path of the electron is diverted, and this diversion makes the flow of electrons or flow of charges, and the flow of charges in this case will be reduced. That is what we call as resistance, and it is the opposition offered to the flow of charges. Okay. And actually the resistance comes into play due to the collision of electrons. When the electrons move from one end to another end, definitely if the conductor has more resistance, there will be more collisions in between the atoms and molecules of the electrons, and therefore the electrons will offer very high opposition to flow from this end to this end. Therefore the current value of the current is highly reduced because of the resistance. Okay. Now also we have studied the relation between current and drift velocity in the previous class, which is given by I is equal to NEA drift velocity, and these NEA are constant, and we can write I is proportional to the velocity of drift. Okay. And there is another important concept, which means that the drift velocity of the electron is strictly related with the relaxation time of the drifted free electrons. Suppose if the electrons are drifted from one end to another end, the relaxation time of the free electrons which are drifted from one end to another end is related with the drift velocity, and the relaxation time is related with temperature. That is, if the temperature increases, the drift velocity decreases, because when the temperature increases due to thermal agitation, the temperature of if the temperature of the conductor increases, what happens to the electrons and atoms inside the conductor? The electrons and atoms inside the conductor absorbs the amount of heat energy, more and more amount of heat energy which is applied to the conductor in the form of heat, and due to which there will be agitation, thermal agitation, and there will be a chaotic situation inside the conductor, so that the path of the electron from one end to another end will not be very smooth. There will be more collisions, and the current flowing through the conductor is also decreased. So drift velocity is related with relaxation time. Relaxation time is related with temperature. Okay. Here, in case of doubling the potential, the current is doubled. We have told when we double the voltage, the current is doubled. And in order to maintain this relation, the value of current should purely depend only on the potential difference between the ends of the conductor. Then only we can say the Ohm's law is valid. So here, if the drift velocity is related with relaxation time, and if the temperature increases, the relaxation time is also related with temperature, therefore the current is decreased due to these factors. When the current is decreased, even though the potential is doubled, the current will not be related as proportionate to each other. So the Ohm's law cannot be valid in such situations. And to explain the statement of Ohm's law, we have to go by current density equation. The current density equation is J vector is equal to sigma into E vector, where sigma is called as conductivity. The conductivity of a material is a constant. Every material has its own conductivity, and therefore if I consider a conductor which is having a conductivity of value 1, then I can say J vector is equal to E vector, then the modulus of J is equal to E. So here the electric field is also written as V by L, because we know the relation between potential and field. dV is equal to E into dx. In such relation we can write V is equal to E into L. So E can be represented as V by L. Okay. Also, by definition of current density, in the previous classes we have dealt about current density, that is J is equal to I by A. If you want to get clear with the current density, you can check on those videos titled current density. We have discussed about the current density and the relation more clearly on those concepts. And by comparing these two equations, I can write I by A is equal to sigma into V by L. Or rearranging the equation, we can have L by sigma A into I is equal to V. Or I can have this term represent V is equal to I into R. So instead of this L by sigma A, I can write R, which is the resistance. So V is equal to IR. So this represents the Ohm's law equation. So the Ohm's law equation can be obtained by the knowledge of current density and the conductivity. Also, we have dealt about conductivity. We have a term which is reciprocal of the conductivity, which is called as resistivity, that is represented by rho. This is the symbol rho, and this symbol rho is nothing but conductivity, and J is equal to reciprocal of conductivity, so I can write 1 by rho into E. This equation is altered, and multiplying this rho with J vector, I can have J into rho is equal to E. Okay, so conductivity is defined as L by AR, and the resistivity rho is equal to reciprocal of conductivity, therefore I can write RA divided by L. So these two are the important relation between the area, the resistance and length of the conductor, which is connected with resistivity and conductivity. Okay. Now, so what is the statement of Ohm's law? At a constant temperature, the steady current flowing through the conductor is directly proportional to the potential difference between the two ends of the conductor. So we have to maintain a constant temperature. That is why we have discussed the relaxation time depends on temperature. Therefore, the temperature, if the temperature increases, the resistance increases, and therefore the current decreases. So we cannot relate with the potential proportional to I. So in order to maintain the relation V proportional to I, we have to go for a constant temperature. So if the temperature is maintained as a constant, then we can say the steady current flowing through the conductor is directly proportional to the potential difference between the two ends of the conductor. And hence we can write R is equal to V by I, where R is the resistance, and the resistance is measured in terms of ohm, and symbol of resistance is here, given here. And similarly, we have another term which is the reciprocal of resistance, which is called as conductance. It is represented by G. It is the reciprocal of resistance, and it is measured in terms of mho. So you have to reciprocate this OHM as MHO, and the symbol is ohm inverse. Okay. This is the graph which is drawn for a conductor. Only this graph is suitable for conductors which obeys Ohm's law. Ohm's law is a specified law which can be applicable only for certain conductors in which the conduction is due to free electrons only. So in this aspect, if we draw a graph between the current and voltage potential, If we increase the voltage, the current also increases, and hence they are directly proportional to each other. The graph is a linear graph, so the slope is always a constant, and the slope is equal to 1 by r. So this graph represents the conductors which obeys Ohm's law. For those conductors which do not obey Ohm's law, the graph will not be a straight line, it will be a curved one. Instead of straight line, the graph will be a curved one like this. Okay, here we have to consider the situation in which the conductor has large number of molecules and atoms inside it, and here these red icons are representing the electrons, and the resistance of the conductor is increased with increase in temperature. Here we have to concentrate on the factors on which the resistance of the conductor depends. It depends on temperature, not only on temperature. The first thing, it depends on temperature. When the electrons collide inside the conductor, due to friction, the temperature increases and it gets heated up further. So here, on heating the conductor, the thermal energy increases, and the thermal agitation of the atoms also. On heating the conductor, the thermal energy increases the thermal agitation of the atoms. Due to thermal agitation of the atoms, the electrons collide with each other, and also the atoms and molecules present inside the conductor, and the situation is more chaotic. So the chaos is more in this case. So due to these collisions, the resistance of the conductor is more. Therefore, if an electron is moving from this end to this end, it struggles a lot to reach. Therefore, the opposition offered to the flow of electrons is very large, and hence we can represent the resistance is directly connected with the temperature. If the temperature increases, the resistance of the conductor is also increased. Okay. When the electrons do not have more space to move inside the conductor, what happens? Suppose if the conductor is very thin, the area of cross section of the conductor will be very small, wherein the chance of collision is appreciably high. Definitely, if the space to move for the electrons is very small, if this area of cross section is very small, if you consider a very thin conductor, thin wire, definitely there won't be any more space to move inside the conductor, wherein the chance of collision is definitely high, and therefore due to collision the temperature increases and the resistance also increases, which increases the resistance. So if the area of cross section of the conductor is very small, the resistance will be high. Therefore they are inversely proportional to each other. So this is the second thing which is connected with the resistance. The first thing we have connected the temperature, R is proportional to T, and here R is inversely proportional to A. A represents the area of cross section. Suppose if you consider a conductor of length L, and this let be the area of cross section, A be the area of cross section of the conductor, and if the voltage is applied in between the ends of the conductor, and if the conductor is cut into two halves, so we can cut the conductor like this also without changing the area of cross section. If I want to cut the conductor, I have to cut along this cross section. If you cut along this cross section, it represents the area of cross section of the conductor is halved. Now the area of cross section is halved, so the current through the conductor is also halved. If the area is halved, the current passing through the conductor is also getting halved. Therefore the new resistance of this conductor after cutting the area into half is given by V by I by 2, that is equal to 2 into V by I, that is equal to, so V by I can be represented by R, so 2R. So here the new resistance, actually the original resistance of the conductor before halving the area is R. Capital R is the initial resistance. After, when the area is halved, the resistance becomes twice the original resistance. When the area is halved, the resistance increases 2 times. The resistance is doubled. Okay, so keep it in mind that if the area is halved, the resistance is doubled. So when the area of cross section is very small, the resistance increases. So they are inversely proportional to each other. And the third thing is that also if the path traveled by the electron is longer, so here we are going to concentrate on the length of the conductor. If the length of the conductor is large, the number of collisions increases, which results in increase in resistance. This is how we can explain this. Here we are going to have a conductor having length L and area of cross section A. Suppose if this conductor is connected to a power supply, the potential difference between the two ends of the conductor be V. Therefore, the current is flowing in this direction. Let R be the original resistance of the conductor for a length L. Then V is equal to IR is the equation which holds to calculate the potential or calculate the current flowing through the resistance flowing through the conductor. If you consider a conductor of length L and another conductor of the same length is attached or combined with this conductor having the same area of cross section A, now the length of the conductor is doubled. In this case, the potential applied to the conductor is V, and here the potential applied is also V. But the current flowing from this end to this end is the same current is flowing through this end because they are combined in this manner. So they are combined in this manner to increase the length, to double the length. So the potential across each conductor is V, and the potential across the total ends, the potential across the ends, total conductor, the combination of the conductor is the length of the combination of the conductor is 2L, and what is the total potential between the two ends is 2V. Therefore, in such situation, the combined resistance, the new resistance, the combined resistance is given by 2V divided by I, that is equal to, again V by I is equal to R, so 2R. In this case also the resistance is doubled. Here the resistance is doubled because of the length is doubled. So I can relate the length and resistance as directly proportional to each other. Thus doubling the length of the conductor doubles the resistance. Okay. Now example problem is given. How to calculate the resistance of an aluminum wire which is having a length 50 centimeter and cross sectional area 2 millimeter square, and the resistivity of aluminum is given. So we know the formula. R is proportional to L and inversely proportional to A. Therefore R is equal to rho L by A. So rho is a constant of a particular material, aluminum. So this data is given, and by substituting the known values we can have the resistance of a particular conductor, which is discussed here, that is 0.0065 ohm. So we have arrived this equation of Ohm's law by making several assumptions about the existence and behavior of the free electrons. These assumptions are not valid for semiconductors, insulators and solutions, because in semiconductors we are going to concentrate also on the holes, which is also the carrier of charges. In the case of insulators, if the temperature increases, the resistance is going to decrease. So we will see this concept on the further videos. And in the case of electrolytic solutions, we are going to concentrate on both the positive ions as well as negative ions. And here in the case of conductors, only the free electrons are concentrated, which are responsible for the conduction. So Ohm's law cannot be applied for semiconductors, insulators and solutions. It can be applied only for the conductors. Okay, so this is a Ohm's law, and how we can able to calculate the resistance, resistivity or conductivity or current density of any particular material is discussed here. So keep on reading, keep on watching these videos. If you have any doubt, please comment, make a comment, make a note. We will discuss those concepts. Don't forget to subscribe my channel Ranganathan Physics for further videos. Thank you.